Okay, so I'm going to end a little bit early, so there'll be time, I swear, there'll be time for questions this time. So the plan is two things, just two things. So one is, what's the center of k-space mean? It turns out the single point at the center of k-space is a really important point that really strongly controls what the image looks like, just that single point. And one of the homework exercises on the second homework is to just sort of mess around with the center of k-space and just convince yourself, wow, you can just like completely change the look of the image by messing with the center of k-space. And what's the center of k-space? That's actually the center of the echo. That's that little point at the center of the echo. That's actually what turns out to be the center of k-space. So we'll talk about the center of k-space. Sort of mess with a cosine brane again, very simple brane, just sort of see in the simplest case what that looks like. And then we'll talk about a complex image. Now, why a complex image? Because the brane is real. And so if everything worked out right, after you do the inverse Fourier transform from the MRI data, you ought to get a real image because your brane is real. It's not complex. Well, it's complex, but it doesn't have an imaginary component to it. But it turns out the actual data that we collect is all complex, really complex. There's big imaginary parts. They're just as big as the real parts. And it turns out every data point basically corresponds to a complex image. So that's what a single point in k-space corresponds to. So this will sort of finally get to the point of trying to understand really what a single point in k-space that we collect, each individual data point in an MRI acquisition consists of. And then we'll try to figure out, like, how come we end up with a real image, even though we've got all these complex data points? And what are the conditions, Hermitian symmetry, what are the conditions that essentially give us a real image? Which is what we want, because our brane is real, and it doesn't have any imaginary parts in the image. Okay, so let's start off with a image that has something in the center of k-space. Because remember the last example I went over with the cosine brane, the center of k-space was empty. There were just two spots in it because there was the positive frequency one and negative frequency one spot, but there's nothing in the middle. So our simple brane is so here's the image side. And here's the k-space side, spatial frequency side, and so we have those same 5 representations on each side. So our brane, our image, is going to be a very simple one. So y isn't on the right side, so that means it doesn't matter what y is. And the only difference is we add 1 to our cosine brane. So, 1 plus cosine of whatever x is. So that's our cosine brane. So what does that look like? So we've got our 5 squares, so we can either be real and imaginary, or our amplitude and phase, or we can think of it as yeah, I see I made a typo last year, so I'll correct it this year. The notes are correct, but there was a typo in the last year lecture. So this is either real image xy or imaginary image xy or amplitude image xy. So this is x and y going here, or phase image xy, or vectors. Just make little vectors. And so if we just plot this function out, what do we get? And again, I'm using light on this glass to indicate dark. So if you look at my notes, dark means lower, and light, which is the white paper, means higher. So that's basically what a cosine looks like, a 1 plus a cosine. And so what does that look? So it just looks like, let's put the x going that way. So it just looks like something that starts at 2 and then goes down to 0 and then back up to 2. So there's 1 and 2 because we added. Normally it goes between 1 and -1. So this is actually, this cosine brane is a little easier to understand because it doesn't have those funky stripes in it because of the amplitude always being positive. So what we did here is the amplitude of this is always positive because we're still having just a real only brane. So the imaginary part of the image is all 0. And so the phase, instead of the phase having some weird thing going on, the phase will all be 0. Pointing in that phase 0 means pointing along the positive x-axis. And so when we look at the amplitude, then the amplitude will basically be just exactly the same as the real image. So it'll be exactly the same cosine amplitude. So that's our amplitude, and so that looks exactly the same as the real. And then here's where I made a mistake last year when I was drawing the arrows. So the phase is all 0. So basically the amplitude is largest at the very edge, up here, and then it goes down to 0 right in the middle, and then it goes back up to a large number here. So that's what the sort of little forest of arrows diagram looks like. And then they get smaller here and even smaller here. And then they're starting to get big again here. So all we're doing is just drawing out. It's just a redundant copy of the data, but you'll see when we talk about a complex image, this will help us kind of visualize what's going on. So they're all pointing in the same direction because the phase is all 0, and they're maximum at the edge. Okay, so that's our and 0 in the middle. So now let's consider the center of kSpace. So the center of kSpace, it's a single point in kSpace. And so if you just draw out the equation for it, so the Fourier transform, let's just draw out the Fourier transform equation again. It's just basically the sum over all x, sum over all space of whatever the image data point is, times e to the minus I, 2 pi times k times x, and then integrated, summed across all of x. So now, what's the center of kSpace? The center of kSpace is just k equals 0. In the case of a two-dimensional kSpace, it's kx equals ky equals 0. But we're just doing the one-dimensional here just for ease. And so if we turn that guy into 0, so that's the center of kSpace. What does that do? Well, like I like to say, I saw this in my previous lecture, 0 is more powerful than I. So if you multiply I by 0, you get 0. So 0 beats I. So what is e to the 0? E to the 0 is 1. And so this whole thing turns into 1, just real 1, real only. So if that turns into 1, now this one could potentially be complex. Complex. And so we would be multiplying whatever the complex vector was by 1. But if the imaginary part was 0, which it is here, because we just defined it to be 0, imaginary part is 0, then that's a complex number that just happens to have a 0 imaginary part, and so it's only real. And so what does this equation say? It just says that the center of k-space, when we set k to 0, so if we set this guy to 0, it goes to 0 over there, we just get the average. So basically the bottom line of this, so what is the bottom line? So center of k-space is average. Space is average of image. Now that could be a complex average, in which case we kind of have to add up vectors, and you might end up with a vector. But it's going to be the average. It's the average brightness, average brightness of the image. So if we go back to our original cosine brane that didn't have 1 added to it, we can see that what's the average of a cosine? Well, the average of a cosine is 0, because there's just as much positive cosine as negative cosine, because it's it's like the positive part will always have an equivalent negative part somewhere in the wave across a cycle, and so the average of a cosine is 0, but the average of this guy isn't 0. So what's the average of this guy? Well, it's going to be 1, because the average of a cosine was 0, and then we just added 1 to it, and so we got an average of 1. And so when we Fourier transform this guy, then we're going to end up with a k-space center point. And so what will that look like in our sort of 5-point diagram? It will just have one more point in it. So here's our k-space with spatial frequency 0, just the single point at the center. And so what is our k-space look like now? Now we've got like a point off to the side. So this was, that's kx equals 1, ky equals 0, and this was, kx equals -1, ky equals 0. But then we also got the center, and the center is the average brightness of the image. Very powerful point. If you mess with that, you can invert the contrast of the image. Like if gray matter was brighter than white matter, you can turn it the other way around if you want. So it really strongly affects the way this kind of has an unusually strong effect on the way the image looks, just to mess with that point. So what does it look like over here? It's all 0 again, because because we started off with just this real only cosine, basically. And if we look at the amplitude and phase image, it will pretty much look exactly the same. So here's the amplitude and the phase image, and here's the vectors. So this is just going to look like the same thing. There'll be a k-space center for the amplitude, and then spatial frequency 1 and spatial frequency -1. And then over here it's just going to be 0 again. And then you'll basically just have an arrow, a positive arrow in the middle with phase 0. And so that's your That's your sort of vector representation of the complex number, which is represented also here and also here. Okay, so that's the kSpaceCenter. So it's the average brightness of the image, and controlling, what the conditions of the data are when we record the kSpaceCenter it's one of the most important things for determining what the contrast of the image is going to be. And we'll often take sort of liberties and record some data with different amounts of echo times. But when we look at what the image mostly looks like, it will mostly look like what the echo time was for the center of kSpace. And so it's not uncommon to mix echo times in our kSpace. And if we do that, that should change the contrast, right? Because that's all the homework problems. How does the contrast change when you change something like the echo time? But you'll see when you fiddle with the center of kSpace, it really changes things a lot. And so a lot of times we pay a lot of attention to the echo time for the center of kSpace and much less attention to the echo time for other parts of kSpace. Okay, so that was the center of kSpace. So now let's consider a complex image. So what does the complex image look like? Well, we'll start with our image again over here. So here's our image. And I need some space up to the side, so some space for the Hermitian symmetry over there. And so this is our kSpace. Okay, so for our complex image, basically we're just going to just remember once again, it's just a complex vector right there, and we've got a real and an imaginary part and some angle and amplitude. In the case of our image, we're going to end up with an amplitude of 1. In a generic image, the amplitude could be whatever. But we're going to sort of have an example where the amplitude is 1. And so, again, we're not going to pay any attention to y. And so what is our cosine brane going to be equal to? It's just equal to the cosine of x minus I times the sine of x. So that's our slightly modified cosine brane. And we also know that as just e to the minus ix. That's the same, those two are equivalent. So, and don't forget, x is serving as an angle here. So x is an angle, and you can see it's an angle because we're taking a cosine of it also. Okay, so what does that look like now for the real and imaginary part of our complex image? So here's our 4 panels again. So we have the real, imaginary, amplitude, phase, vectors. So the real is just a cosine. So cosine, let's just draw it out here. So it starts at 1, goes to -1, back to 1. And our imaginary part is going to be a sine. But it's a minus sign. And so we know that when we make a minus sign, it's just going to be an upside down sign like that. Okay. And what does the image look like? So the cosine image is the most negative in the middle, just like it was before. And then the sine normally would be sort of like a quarter of a cycle over, but now it's, we took the negative of it. And so the most negative part of it will be a quarter cycle to the left instead of a quarter cycle to the right. And it sort of gets lighter here, and it's lightest there. It starts to get a little darker there. Okay, so that's our complex image. So now we've got an imaginary part to the image. And so what does the amplitude look like? So what is the amplitude? It's just 1 of this very simple cosine branch. So it's completely uniform. So the graph of the amplitude, so this is 0 and that's 1, 0 and 1 up there. So the graph here, it's just 1. So there's 0 and 1. It's uniform across the whole thing. And then what does the phase look like? Well, we can sort of, if you look at this one, it's simpler. It's just going to be an increase or decrease in this angle because there's a minus in front of it. And so what the phase is going to look like, it's going to start at 0, and then so that's 0, and it's just going to go down to basically, minus 2 pi, 360, minus 360. And so that's just going to look like just a ramp. So it's darkest at this end, and then it slowly increases. So it's lightest at this end. It just gets darker and darker, so it's just a uniform ramp. So importantly, what does it look like when we draw it out like arrows? Well, it's going to be 0. It's going to be 0 phase at this point, and then we're going to be going negative. And it'll be 180. Like at this point, that's pi right there. So it'll be 180 degrees phase in the middle, and then we'll be back to 0 over here. But the arrows now are all the same length, and so they're turning negative here. So here they're going to turn negative this way, and then, continue negative that way, and then be a little bit less that way. And we're still going in a negative angle direction, like that. So that's what the arrows will look like. So they'll all look like, so right in the middle, they'll all be minus 180, and then they'll sort of rotate in a negative angle direction as we go right across the image. And then they end back up at 0. So that's what the simplest complex image that we could think of. So amplitude 1, and it's just a sine plus an imaginary cosine, which is just going around the circle. Draw them all in there so we can see all these little spins, all little spins. So it turns out this is basically what a gradient does. This is exactly what a gradient does. So what's the kSpaceCenter here? So remember, the kSpaceCenter is stick in 0 for k. So if you stick in 0 for k, you're going to be multiplying by 1, by real 1. But then your image that you're summing up in your Fourier integral is all complex. But if you look at these guys, what are they going to do? You have to add them all up. And what do they add up to? Well, they add up to 0. So the kSpaceCenter in this case is still going to be 0 because all those vectors will cancel out. So if we draw our Fourier transform picture over here, what is that going to look like? So it'll look quite simple. So this is our kSpace. So it's going to have basically just one point in kSpace. So there'll just be one point there. And here's where the other point would be, but it's not there. And what is the phase? The phase is going to be 0 of that point. And what is the... So here's real and imaginary. And not the phase, the imaginary part is going to be 0. Imaginary part over here is going to be 0. And the amplitude is just going to be the same as real. So there'll just be one point over there. And the phase will also be 0, all 0. And when we get down to to our complex picture, we just got one vector with 0 phase. So this turns out to be what a single point in kSpace actually looks like. It looks like a complex image. So every single point in kSpace corresponds to a complex image that has a large imaginary part. And yet, when we look at our image after we reconstructed it, we should have no imaginary part. And so how do we get rid of the imaginary part, given the fact that every single kSpace has a substantial imaginary part? This one just doesn't happen to have a substantial imaginary part, but if we actually look at any typical MRI data, I happen to give you an example of one that didn't have an imaginary part, but if we look at any MRI data, you can have the imaginary parts of the data are just as big as the real parts of the data. And so how do we sort of get rid of the imaginary part? Let me just put a note down here. So when we did our center of kSpace, center, equals a complex number, across X, complex times 1. But that turns out to, equal 0 because they're all distributed evenly around the circle. Okay, so to explain why, what is the property of kSpace? It's a symmetry property of kSpace that happens when you have a real image. So this is a complex image, but if you just have a real image, go back to Wednesday and look at a real image, there's a certain symmetry to kSpace. So that symmetry was, we noticed there were 2 points, but it's more complicated than that. So it's something that's called Hermitian symmetry. Hermitian symmetry. So kSpace doesn't have to have Hermitian symmetry. But if it does, then you'll get a real image. And so we'll sort of just go over what the Hermitian symmetry is and why it gives you an image that doesn't have any imaginary parts to it. And so we could do it so if you do it in 1D, start off in 1D, what is Hermitian symmetry? Hermitian symmetry is so we're using capital H to mean we've done a Fourier transform, so we're in the frequency space. So if we take the negative of the spatial frequency argument, it equals the complex conjugate of the positive frequency argument. So now, if you're like me, complex conjugate, oops, that's, I don't know what that means. What does that mean? So what is the complex conjugate? So the complex, we've already done the complex conjugate sort of multiple times. So, whenever we look at something like that versus the negative angle, that's basically the complex conjugate. And so what is the complex conjugate? It just means a complex number where the imaginary part has the opposite sign. That's the meaning of it. So, complex conjugate. It just means, imaginary part has opposite sign. So, what's an example? It could just be, say we have an imaginary, number like 3 plus, 4i. So what is that? Well, that's like 3 plus, 4i. It's like that number right there. And so what is the complex conjugate? It's just 3 minus 4i. And what's that? Well, that's this number here. So this is minus 4 over here. So that's all the complex conjugate is. So that's what this thing means. Well, mathematicians, star could mean about 17 things, but in this case, it means the complex conjugate. And so what does that mean? So that means that if we just have a one-dimensional, Fourier transform, it just means that if here's 0, so we're always embedding this extra sort of xy inside each point. And so if we go to some particular k, so here's like, k equals, say, 3, and here's, k equals minus 3. So what's embedded in there? Well, there's going to be a real and imaginary embedded in there. And so if this guy happens to be, I'll just use that example, 3 plus 4i. So say that the value at that k-space point happens to be 3 plus 4i. What does this equation say? This equation says that this point over here has to be 3 minus 4i in order for it to be an example of Hermitian symmetry. So as long as when you go to the negative k equivalent, you always find a number in which the sign of the imaginary part is opposite. So it works both ways, because if I had 3, if this guy on positive, k was 3 minus 4y, then this one would have to be 3 plus 4i. So it could go either way. So that's Hermitian symmetry for 1D. It's a little more complicated when we have it in 2D. So in 2D, it looks like the Fourier transform of minus kx, comma, minus ky. So now there's two variables for this function is going to equal the complex conjugate of, again, two variables there. So what does that mean? So this guy meant that. So what does it mean in our two-dimensional k-space? So this is, again, the problem in understanding this is just keeping all these dimensions, you got x and y in the image, and then, but at each point, you've got another sort of x and y embedded in there, which is like this complex number. And then you have the same thing in kSpace. So you've got, remember the dimensions here. This is the k, x direction in kSpace, and this is the ky direction in kSpace. So what does the Hermitian symmetry look like? Let's draw a bigger kSpace down here so we have some room to write. So what it means is kSpace is, with a real image, kSpace is kind of redundant. So what this second equation means, so this is, that's kx going in that direction, that's ky going in that direction. So what it means is, if we take a point right here, so what is, let's just use the 3, 4 example again. So say this guy, now let me do, so say this guy is kx equals 7, ky equals 2. Okay, sorry, not that point, but this point right here. Okay, so we go out k. Let me just write the coordinates along. It's very easy to get confused. I've confused myself many a time. So here's, kx equals 7, and then here's ky equals 2. Okay, so that point right there in kSpace, if we take the complex conjugate of it, which is reversing the sign of the imaginary part, it should be the same as minus, kx equals minus 7, ky equals minus 2. But the problem is, just make sure that we distinguish what we're talking about. So at this point right here, there's going to be an imaginary number, an xy imaginary number, and say that is 3 plus 4i. So don't get the kx, ky mixed up with the actual value of the data point at that point. So at kx equals 7, ky equals 2, the value there is 3 plus 4i. And so what does this compact equation say? It says that if we go to kx equals minus 7 and ky equals minus 2 to that point. So that should be, I didn't draw it out quite far enough, but let's draw it a little further. There we go. So this is ky equals minus 2. So that point, it's just the sort of mirror image across the middle like that. That one should be 3 minus 4i. Okay, so that would be a case of this special Hermitian symmetry. And how does that work? Why does that get rid of the imaginary part? Well, if you just go back to the Fourier transform equation, we basically are summing up. So we're thinking of it as inverse Fourier transforming kSpace back to a real image. So how do all these points in kSpace with large imaginary components, how do we get rid of the imaginary components? And so now we're summing across spatial frequency, and here's our kSpace points, because we're doing an inverse Fourier transform now. And so it's kSpace points as a function of k multiplied by our, e to the I 2 pi k times x summed across all kx, and that's going to give us our function at a point. So we're summing across all spatial frequencies, all kx's, in order to get a single voxel, single point. So a single point is a sum across all spatial frequencies. So how does this Hermitian symmetry help us? Well, so we're basically summing all of k-space. We're sort of to make one voxel, we're doing this sum across all of k-space, but it has the particular property that the numbers that we're summing always cancel out their imaginary components because we have this symmetry condition in k-space where the negative frequencies always have the complex conjugate, and the complex conjugate means you have the opposite sign on the imaginary part, and so when we add it up, it goes away. So what is that? So what does that imply? So that implies what's going on. You've got a whole bunch of imaginary data that's going all over the place, in the real imaginary plane, like this. But magically, because we've got this Hermitian symmetry, what happens is, in the end, when you add the whole mess up, we end up with something that doesn't have any imaginary component. So here's the imaginary, axis, and here's the real component. And why does that happen? It happens because we always are guaranteed that the negative frequencies are going to have a number at that negative frequency spot that has an opposite sign to the imaginary part. So that's why, that's how we can sort of collect k-space data, all of which is complex. It all, it corresponds to a complex image, and it has a real and an imaginary part. And then when we Fourier transform it, somehow we erase all the imaginary parts, and we just end up with a real image. So I didn't get here. It took me years to finally figure out, what is one point in k-space, corresponds to? It corresponds to this weird thing here, something that a gradient does. And then how do you get rid of the imaginary parts? Well, you've got this special symmetry. You can see that k-space is redundant, and so that means you don't have to collect all of k-space because, this point is going to be equal to the complex conjugate of that point, and so those points are going to be equal to each other, and this point is going to be equal to that point. So you only really have to collect half of k-space, and you can do that on the scanner. You can say, just collect half of k-space, and then fill in the rest of it by substituting in the complex conjugate of whatever the data that you collected was. Because it's redundant, because that thing shouldn't be the same value, but it should be the same value with the imaginary sign flipped. And so all of these different points will all be, the same thing will apply across here. So this point should be the same as that point with the sign of the imaginary part flipped. Now, when you collect data from the scanner, does it have Hermitian symmetry? No, it doesn't. It's not forced to have a Hermitian symmetry because k-space can be whatever. You can just stick random numbers into k-space and do a Fourier transform and see what you get. Or you can stick noisy numbers. You can Fourier transform an image, inject a bunch of noise so that it no longer has Hermitian symmetry, and then un-Fourier transform it, and you'll get an image. But that image is going to have an imaginary part to it. And so how do we typically deal with this? We just convert it to amplitude and phase and throw away the phase. And so that's what you see on the MRI scanner. So you collect data. It's supposed to be Hermitian, supposed to have this kind of symmetry property, but it doesn't. there's all different kinds of imperfections. And so we typically end up with a complex image. And then we just convert it to amplitude and phase, throw away the phase, and just look at the amplitude image. And that's sort of essentially these vectors. They're supposed to all be along the x-axis, but they won't be. And so instead, we just take the length of the vectors, show that, and then throw away, whatever random angle they had that corresponds to a spurious imaginary component. So that's the Hermitian symmetry, and how we essentially end up getting rid of, canceling out all the imaginary components in order to get a real image. And then it's also like this is what our raw data is. Essentially, our raw data is complex valued things collected from a real brain. So it's a real brain, but we're collecting complex valued data from it because we've got phase sensitive detection. We're getting 2 numbers out of each data point. And so we're collecting complex valued data out of the brain for each point, which is a single point in k-space. And then hopefully that complex data will have Hermitian symmetry so that when we Fourier transform it, we can get something back that's all real, but it typically isn't. So we just do this hack of just looking at the amplitude part and throwing away the phase. Because if we just looked at the real part, it would look like a mess. The amplitude image will look pretty much the way it's supposed to. This one is just going to look like it will completely vary depending, like if the vector was supposed to be like along the x-axis like this, but it had a big imaginary component like that. Instead, same length vector, the real is suddenly going to go to 0. So the real image, if you don't have Hermitian symmetry and you do an inverse Fourier transform, you'll get a real image that just looks like completely uninterpretable. Okay, so what we'll do, I stopped before the very end. So what we'll do is next week is basically go over how the scanner does this. How does the scanner essentially do this to your brain, so that one of your data points is a single point in k-space. And so there's time for at least 1 or 2 questions about center of k-space and or complex image and or the Hermitian symmetry. I think I did it a little clearer this year to clearly distinguish where you are in k-space from what's actually there. So where you are in k-space, you need 2 coordinates, kx and ky, and then what's there, you need 2 coordinates, which is the real and imaginary. So any questions out there? One little question, even going back to the very beginning is okay. It was all super clear. I don't believe that. It was better than last year. All sort of good. Not too bad. Going. Yeah, there's a lot of things in here, a lot of concepts piled on top of each other very quickly. So let it marinate for a while, and if something, when you go back and you get lost, definitely ask some questions, and we can, over the next weeks, we can easily sort of go back to any of these things. But we'll essentially review the basic idea multiple times over and over from slightly different vantage points. Okay, well, I think I'll call it a day.